Welcome back. So this is one of the first of several videos where I'm just going to work through a lot of kinematics examples. They're in no particular order, and I'm just going to go through them, try to explain my reasoning. We'll use the formula sheet from the course, the one we're looking at right now, and I'll try to make it clear why I pick the formulae that I do and just get you used to doing this so that you can do it comfortably when it comes up in Physics 30. Um, I'm certainly going to make some mistakes, and it won't even be on purpose. It'll just happen, and then we'll see, hopefully, that I will notice those and will recover from them and carry on, because physics is like that sometimes. So let's get in there and tangle with some problems. Okay, so what is the average velocity over the entire 10 seconds? What they're showing us here is some object was moving. The clock started at 0 and then 2, 4, 6, 8 up to 10 seconds seems to be where the story ends. And at first the object was going fast. It was going 30 meters per second. And then it slows down to just 10 meters per second. If you watch my previous video, we actually did this question already, but we did it with just the numbers given to us. The only thing different here is that we're having to read them off of a graph. So there are two different intervals here. We have one here where the velocity is 30 meters per second, and the elapsed time is, the clock starts at 0 and we go over to 4 seconds. So a total of 4 seconds passes in that first interval, and we have a formula that says distance equals vt. What it actually says is velocity is distance over time, but I'll probably say this half a dozen times in the next little bit. We often multiply both sides of that equation by t. Those cancel, and then we get the version that I carry in my head, distance equals velocity times time. So if we follow that, our distance is v times t, so it's 30 times 4. It's 120 meters. Whatever this object is, it goes 120 meters in this first interval here. Then everything changes. The velocity suddenly drops down to 10 meters per second. So here we have v equals 10. And the elapsed time here, well, we go from 4 seconds up to 10 seconds. That's a difference of 6. T equals 6. Remember, in the original formula, they write delta t. That's what they mean by this. They mean how much did the time change. We don't care that it got up to 10. What we care about is it went from 4 up to 10. That's a difference of 6 units. So delta t means the difference in the time, or how much the time changed. So if we take that and we do distance equals vt, we get 10 times 60, sorry, 10 times 6 is 60 meters. Okay, good. None of that answers the question yet, but we're getting closer. What they want is the average velocity over the entire trip. And we know you can find average velocity by doing your distance divided by your time. Now, this chunk had its own velocity, 30, and this one had its own velocity, 10. The average velocity for the whole trip is going to be the total distance divided by the total time. So our total distance would be 120 meters there plus 60 meters there is 180 meters. Over the total time is 4 seconds for this first chunk, 6 for the second, total of 10 seconds. 180 divided by 10 is 18 meters per second. Okay, another graph. They want the magnitude of the object's average speed again during its first 4 seconds of travel. So again, there are two intervals going on here, and I'll color code them so we can keep track. This is a section where everything's behaving consistently From 0 to 2 seconds, because that line is straight, we know that the object was going at a constant speed that whole time. Anytime you have a distance time graph, the slope, like we call it in math, of this line tells us how fast the object is going. So a constant slope, a line that isn't curving, tells you you're going at the same speed through this entire interval. Then the speed suddenly changes, and then here the speed changes again. So there are 3 different speeds shown on this graph, one for every section of line. The first one goes up to 2 seconds, and, sorry, red. Then we have a second interval from 2 seconds up to 4, and we aren't actually going to use that last interval because the question only asks about the first 4 seconds. So, what's the displacement for the object in this first section? We know, sorry, let me skip ahead a moment. If we're going to find average speed, like in the previous problem, we know that average speed comes from doing your total distance over the entire trip, in this case the total 4 seconds, over the total time. So we need to get both of those things. We need to know how much distance was there in this first interval and how much distance in this second one. And because we have a graph, we can just read those numbers off of it. In this first section, we go from the 0 meter mark up to the 8 meter mark, so our distance there is 8, or our displacement is 8 meters. And the time in that first interval, the clock goes from 0 up to 2 seconds, so that's a distance, or a delta of 2 seconds. Fair enough? In the second interval, we start out at the 8 meter mark and nothing happens. We end up at the 8 meter mark. A flat line like this means you didn't move at all. And so here we'd have to say our distance or our displacement is 0 meters. So whoever this was, they moved forward for a bit, got to 8 meters, then sat down and had a rest. Well, it was 2 seconds, so they briefly stopped to rest. And then in this section, not that it matters, they actually moved backwards. They went from the 8 meter mark back to 0. So if we were doing this one, we'd call the distance minus 8 meters because it went down from 8 to 0. But over this interval, the one we're looking at, we went from 8 to 8, and so for displacement, we say there wasn't any. But some time went by. The clock was still running. The time went from 2 seconds up to 4 seconds, so our delta t there is 2 seconds. So our total distance would be 8 meters plus 0 meters is a total of 8 meters. Our time is 2 seconds plus another 2 seconds makes a total of 4 seconds. 8 divided by 4 gives us 2 meters per second for our average speed. Okay, new thing. We haven't talked about acceleration yet, but it's happening now. When a gun is fired, a bullet accelerates through a barrel a distance of bleh and exits with a speed of bleh. If the gun is parallel to the ground and the bullet travels for this many seconds, the distance covered by the bullet is oh, okay. Maybe we don't need the acceleration for this. Again, there are 2 sections of this, but they only seem interested in one of them. Here is a gun barrel, not to scale, and inside it we have a round that sits back here. Behind it there's some kind of propellant, and the first thing that happens when the propellant is ignited, the round accelerates a lot until it gets to the end of the barrel. There's trapped gas in the barrel behind it, pushing it along, and so it gets this very high acceleration. They don't say how much, but there is an acceleration here. The round travels a distance of 0.855 meters. That's the length of the barrel. And its velocity goes from 0, that's the initial velocity when it's just sitting in the chamber, to a final velocity of 457 meters per second as it comes out. That's what they call the muzzle velocity. It's how fast are you going just as you exit the barrel of the gun. So all that happens before the round actually comes out, and then there's a second interval where it flies through the air. Starting from the muzzle, the round continues to fly horizontally. And if we're looking at this interval, we would say that the initial velocity is 457. We start with 457, and then they say it flies for 0.638 seconds, and then I guess it hits something, and they want to know how far did the round have time to travel in 0.638 seconds. Well, okay, after all that, it turns out the formula for this is still very simple. It's distance equals vt. All the complicated stuff with the acceleration happened inside the barrel, and I don't think that's what they actually want. They just want how far did it travel after leaving the gun. The velocity is given as 457 meters per second. The elapsed time is 0.638 seconds. And if we multiply those, 457 times 0.638, I should say, I get 291.566 meters. Now, let's be good about sig digs for a moment. We used this velocity, which has 3 significant digits, and this time, which also has 3, so this should be trimmed down to 3 significant digits, so just 292. Our finished answer would be 292 meters. No need to go to scientific. You can write 292 with 3 digits, no problem. Okay. Wandering backpackers being chased. So, sorry, just before we get away from this one, it's important to organize all your stuff and to draw sketches. I encourage you to do a lot of that because especially in problems like this, we gave you an awful lot of information that you do not need. We talk about an acceleration that never got used. There was an initial velocity that we never touched, and there was a distance, the length of the barrel, that we ignored also. So if you just throw all those numbers in a big pile, it can stress you out because you feel like you're missing something, not using this information. You need to break things up into stages and make sure you understand what the stages are. In this case, there's a accelerating down the barrel stage, and then there's a flying through the air stage, and they behave very differently. We'll see that over and over again, but just to introduce that idea, organize your info. We often give you too much. Okay, what's happening here? Backpackers being chased in a straight line by a bear in a park. The backpacker can sprint at 6 meters per second. The bear can run at 8. That's not good. If the shelter is 50 meters away and the bear is 18 meters behind the backpacker, the difference it takes for the backpacker and the bear to reach the shelter is... Okay. There are 2 separate things going on here. Over here is a shelter, and we have a race going on with 2 racers. We have our person, who they say can go 6 meters per second. That's not very good for an adult. Maybe it could be a small person, or they could be in deep snow or something. And the person is going 50 meters. So our velocity is 6 meters per second. Our distance is 50 meters. While at the same time, we have our bear who is faster. Their velocity is 8 meters per second. but they have to go further. They start out 18 meters behind the backpackers. So for them to get to the shelter, they have to cover 18 meters and then another 50, overall 68 meters. Okay, I'm having trouble fitting it all in here, but they'd have to go 18 to get to where the backpacker starts and then 50 more, so 68, fair enough. And the question is there going to be a mauling or is there not? And we need to find out how much time it's going to take for each of these creatures to get to its destination. For the backpacker, we have our formula distance equals VT, or I keep saying they actually give it as V equals D over T, but this form is better. If you want to solve this for time, what do? We want T alone, but right now it's multiplied by V. How do you unmultiply something by V? Answer, U divided by V. If you do that on both sides, these V's cancel, and we get time equals the distance you have to go divided by your velocity. That tells you how long a trip will take. So for the backpacker, it's, I'll say T, oh no, B is for bear. I'll say H for hiker or for human, whatever you want. The time for the human is their distance divided by their velocity, so 50 meters divided by 6 meters per second comes out to 8.33 seconds. That's how long it'll take them to get to the shelter. For the bear, time is also distance divided by velocity, and I'll put TB here for time for the bear. The distance is 68 meters. The velocity is 8 meters per second. 68 divided by 8 is 8.5 seconds. So the backpacker will get there first, but they'll get there first by like 1/6 of a second. So unless they can not get through a door and slam it in 1/6 of a second, there might be a mauling taking place here. The difference in time that it takes would just be 8.5 minus 8.33. So the time difference would be, comes out to 0.166666666 seconds. Oh, and they like to do this with numerics. They ask for the answer in scientific notation. If you put this in scientific notation, you have to move the decimal one step to the right. And so you'd give this as 1.66666 times 10 to the minus 1. The minus 1 is because you moved the decimal one step to the right. It's like you're saying, this is 1.666, only one step smaller, actually. And if you were giving this as a numeric response, we don't do this a lot, but they're saying, tell us the number before the decimal, then tell us the number after the decimal, then give us the power, the times 10 to the how much. So for this, first, if we were giving this to two significant digits, we would round to 1.7 times 10 to the minus 1. And so the numbers they're asking for are just 1, 7, and 1. So in the numeric response, you just put 171, and that would be the answer. Little awkward, but they do that fairly often, so you might see that again. Oh, what's this? LRT draws. Okay, a train starts from rest at Clairview Station, accelerates for a while, and then gets to constant speed. Calculate the train's velocity. Okay, so here we actually are going to do an acceleration for the first time, and then they want a graph. All right, so what all have they told us? They say that this train is accelerating at 4 meters per second squared, so the acceleration is 4. And it does that for 6 seconds. And they tell us one other thing. They say the train started from rest, which means its initial velocity was 0. And they want to know how fast is it going at 6 seconds, which was to say, what is its final velocity? What velocity does it end up at after those 6 seconds have gone by? So we need a formula that can do all that stuff. And I will tell you right now, this one is not on the sheet until we do a little work. Let's go back to the sheet and I'll tell you what I mean. This is one of my favorites, and it isn't on the sheet, but it's so good that I'm going to try to convince you to learn it. If we start with this says acceleration is how much did your velocity change over how much did your time change. So let's grab that and we're going to do some stuff to it. Okay, so this starts as acceleration is delta V I meant to write, over delta t. So first tweak, the change in velocity is, you find that by doing what is your final velocity minus what is your initial velocity. Okay, what speed did you end up at minus how much of it did you already have. So if you started at 30 velocity and went up to 36, you'd do 36 take away 30, and that would tell you that your delta V was 6. Fair enough. Now, I'm not going to do that for the time. We generally don't bother. I'm just going to leave that as t for the elapsed time. And now I'm going to multiply both sides of this by t. Multiply by t, multiply by t. Why did I do that? Because these t's will cancel. So that gets us at equals vf minus vi. And my favorite form of this, I take this vi over to the other side and it becomes positive. So the finished version, which I love, and I think you'll love it too, vf equals vi plus at. This says your final speed is going to be whatever speed you had to begin with, plus whatever extra speed you picked up by accelerating. So this is equivalent to this version, which is on the sheet, but I'd say write this one in, and I think we're going to use it enough in the next little while that you'll end up pretty much memorizing it. It's very, very valuable. I'm a big fan. I hope to make you a big fan also. And it's going to absolutely rock this problem, because they're asking us for VF. There it is. They've given us VI. They've given us A. They've given us T. You're thinking, oh, he customized this formula to fit this problem. No, this is actually how I have it memorized, and it just happens this formula is so awesome that a lot of problems give you exactly this information. So the credit does not go to me for planning this. It goes to this formula for being excellent. And so all we have to do now is VF equals VI 0 plus A 4 meters per second times T 6 seconds equals 24 meters per second. So our train started at 0 velocity, it sped up to 24, and then they're saying it just cruises at 24 for the next 45 seconds, and then something happens. So what was its velocity after 6 seconds? 24 meters per second. Then they ask us to graph what we just said. So we know when the clock started, we had no velocity. The train was sitting still. We know that in 6 seconds, the velocity got up to 24. So at the 6 second mark, we should be 4, 8, 12, 16, 20. We should be here. So we started with no velocity. We speed up to 24. And after that, they just cruise and the velocity stays a straight line. So our graph should just look like a straight line up to 24, and then constant velocity looks like this. This means your speedometer is not changing. Your speedometer read 0, it climbed up to 24 meters per second, and then it just stayed flat. This doesn't mean you're not moving, it just means your speed isn't changing. It's like when you're cruising down the highway. Fair enough. So pencil this in on your sheet or have it tattooed on your arm or something, and I guarantee it'll come up again. And I hope you become a fan like I am.